Hello, everyone. You may remember my theoretical attempts to disprove the Riemann hypothesis. Actually, I've got two disproofs for this fact using the universality theory. Um, so now I would like to present a numerical counterexample, since I know that this claim is quite controversial. To do this, I've built a neural network, which basically finds the potential zero of Riemann zeta function, and after that, we're just numerically checking this zero. So that would be our plan. Since the development of universality theory inspires us to apply it to building of neural networks and potential artificial intelligence, potential AGI. It was nice to try using the simple artificial intelligence, simple neural network to build a counterexample. I consider this to be quite cool. So, what do we start with? First of all, for starters, we know that Riemann zeta function is representable as an Euler's product, where this product is taken over all of the primes. So what do we know? We know that this product is convergent for real parts of S greater than 1 for that region. But we also know that partial Euler products could also show a kind of regularity in the critical strip. It is quite an important statement which actually connects Riemann zeta function to prime numbers and which is also discovered here. Uh, like in this paper of mine, where I have discovered certain approximation properties of those Euler products, mainly partial Euler products. So it is used in the actual proof of the theorem. Yeah. Uh, right here. So if you are interested, you are most welcome to study the theoretical foundation of my thought. But for now, I shall just run really quickly through this. So what would be our goal? Our goal is to take an Euler's product for a large number of primes, and then theoretically prove that it does not differ so much from the actual value of Riemann zeta function using some numerical tricks. So first of all, what should we need? First of all, to minimize the product of such terms, we need to maximize the absolute value of each of those terms, which is done by choosing an imaginary part, so such that it happens that imaginary part of S multiplied by natural log of p is approximately pi for mod 2 pi for the most for as many terms as possible. So we know that we shall always have something like that due to lemma 2, which says that if the multiples are linearly independent with respect to the field of rational numbers, then we've got this. But basically, it means that we can approximate any any of such point with a certain translation. So our goal would be just to find it. Uh, so here is the description of step one, and let us go for the code realization. So further. So here I should note that I was using TensorFlow. You could also use PyTorch or something like that. But for our purposes, it is quite enough. Here we normalize the data, uh, um, define a function for tau prediction, and also we add this counter integral check. It is it is based on Cauchy integral theorem, which is right here. It says that if the function is strictly holomorphic, is on some domain, then the integral over each closed loop of this function should be zero. So what is our idea? If the reciprocal of the zeta function has got a singularity point, then Riemann zeta function has got a zero at this point as well. So since you know that we are restricted from the division by zero, and thus we have a hole in our simply connected domain where our reciprocal of Riemann zeta function is not holomorphic anymore. So we shall use this to pick our candidate. And guess what? And it allows us to find a nice candidate, which is right here. Uh, we also test that the value of this partial Euler's product is small enough, and after that we perform this integration check, and you see that the integral value is strictly non-zero. So what should we do to study it further? To study it further, we take some more prime numbers. So we take all of the prime numbers up to this number, 12 to the power of 8 and plus 17 to the power of 5. So this number does not mean like anything or there is no great revelation about it. It's just due to due to Collab computational powers. Since you see, since for greater powers or for greater base, I've got memory deprecation. So to avoid the memory deprecation, I've chosen this number. So this number is obtained by some serial experiments, and we would like to add some more prime numbers. So we've got this 17 to the power of 5. Yeah, there is no huge sense by picking exactly 17, it is just my favorite number. So it was like this. And after this, after checking the partial oil product for approximately 22.9 million of first prime numbers, we obtain this value, which is quite small, actually, which is astronomically small. But now we need to verify that it is actually a zero. So we take as a strict integral check by using Cauchy's integral theorem as before. I shall show you those code snippets. So here is the snippet for our computation of value of the oil's product. And here we've got a snippet for computation of our counter integral. So we use the SciPy numerical integration. I know that it is not quite accurate, but it would be enough for our demonstration. So we've got this this integral with respect to the border of the disk neighborhood of the given point of this radius of the radius 0.1 and 0.1717. So as we can see, even the slightest change of radii changes the value of integral tremendously, which suggests that there are many more zeros of Riemann zeta function in the neighborhood of this point, and we could also almost exclude the probability of just finding some numerical zeros and the flaws of numerical computation, which is quite good for our purposes and supports our supports our assumption about finding an actual zero at this point. So it is like this. So for the step 4, we need to estimate some errors. So for estimating the errors, I use this formula, this form of analytic continuation of Riemann zeta function to the critical strip. Actually, it was first met in the video by Arik Bekzat-Kanania, aka Riemann's last theorem, and it is basically here. We had a lot of the discussions and troubled communications about his methods. So I don't think that I'm actually gonna get this $10,000 reward. But you've got the complete script of checking this numerical zero, so you could come up with another zero just by yourself. Since my neural network is trained on the randomly generated data, I expect you to find something else, and after that you would just know what to do, and who knows, maybe you shall get this $10,000 reward. So I hope so. But let's get back to this. So, to estimate the absolute value of Riemann zeta-function at this point, we use the triangular inequality to split it into two terms. First of all, is the error of the sum approximation and the actual sum approximation. Since we've got astronomically big range for our prime numbers, it would be useful to approximate this sum representation by the product or representation. Just to avoid some memory deprecation and just to save our computational powers, since you know the quantity of prime numbers is much less than the quantity of natural numbers. Like the density is quite different. So we are doing something like this. Uh, and to estimate the difference between the sum and the product, we want to use the following observation. First of all, we observe that this Euler's product is just a product of a few geometric series, and each natural number is actually a product of some powers of prime numbers. So if we expand each of those sums and look at those look at our look at the terms of our sum just by picking each exactly one element from each of those products of each of those geometric series, we would actually find that our error should be not um should not be greater than this for each of the for each of the geometric series which generate sum representation. So as we know that b is our upper bound, so the product of the terms corresponding to um corresponding to the to the upper bound would be at least b, the product of the powers of corresponding prime numbers. So, and we also know that we would have no, not no we would have a number of those products which generate our error. The number of such remainders would be not greater than b. So since you know our product is generated by picking some terms of some terms for prime numbers which do not exceed b. So we've got something like this. And we've got this error estimate for their sum minus their prod. Oh, and also we know that the b to the imaginary power does not change the picture for the absolute value due to the Euler's formula, which is basically here. So we know that the absolute value of a real number raised to some imaginary power would be of the absolute value 1. Those are basics of complex analysis, so I shall not dive into it. And now we are going to define our estimate between their and their sum using the formula before. Yeah, here it is. So what shall we do? We shall just bring this sum to the left hand side, and after that we'll just take the absolute value of both parts and split it by a triangular inequality, and we obtain this. So we obtain this number and this number. Since we've got since we've got the extremely huge value of our imaginary part, this this guy just goes to zero, like meaning that becomes very very small. And so since we've got an insane oscillation due to the big value of imaginary part, this integral also becomes close to zero. So that is the idea. And after that, we shall just add all of our errors and obtain that the estimate for the maximal value of absolute value of Riemann zeta-function at this point is this small number, which is besides less than the machine epsilon for Python for the standard Python computations divided by 1000. So to see how it works, let's just let's just run it. So well, here we've got our S candidate. Here we've got our product value, and here we've got our B. So I would also note that for estimating of the integral term, we had to split the integral by the additivity of integral by for two integrals, one from b to b multiplied by 10 to eighth power, and from b multiplied by 10 to the eighth power uh up to infinity, just by using just by using the triangular inequality plus the additivity of integral. So here let's see what we've got. I shall show this this computation, since it is relatively quick. So now, yes, and we've got what we have expected. I shall not show the previous computations, since they took almost a lifetime to be performed. And for the bonus step, we would like to check the symmetrical brother of this of suggested S, and the value of the zeta in the point 1 minus S. It should be also a zero. So if we would have some problems with that, it would ruin our counterexample. But in our case, we are lucky, and our counterexample is well supported. Let's check the Riemann functional equation, which is right here. To compute the value at the symmetric point, I just use the Riemann's functional equation, and just by knowing the approximation of zeta at our point, we could get the estimate for the symmetric point as well. And what do we have? Um, in this realization, we've got an astronomically small value of the Riemann zeta function, of absolute value of Riemann zeta function, which fully supports our numeric counterexample. And if we compare this number to something, just imagine that this number is less than 1 over the number of atoms in the universe raised to the 10th power. So it is very small value. That is why, assuming that there were no computational errors, just in the constructions of the libraries like SciPy, MPMath, and NumPy, we can conclude that we've got a fully justified numerical counter example. And once again, to see why it works, please follow the video with a theoretical argumentation. For and just before we finished, I encourage you to find your own counter examples. Please leave in the comments leave to the comments anything what you would obtain using this script. I shall leave the link to this script also in the description. So for today, it is all. So thanks for watching, and remember, the best is yet to come.